Hello, my name is Jeff Buffkin, and today we will be going over the proof for Euler's criterion, which says that for an odd prime and the number a such that the GCD of a and p is equal to 1, we have a raised to the p minus 1 over 2 equivalent to the Legendre symbol, which is 1 if a is a quadratic residue, -1 if a is a quadratic non-residue, and 0 if p divides a. However, since the GCD of a and p is equal to 1, this is an impossible case because the GCD of a and p is equal to 1, because if p truly divided a, the GCD would be equal to p. Now, quickly, we're going to recall a couple earlier results. Firstly, Fermat's little theorem, which states that for GCD of a and p equal to 1, that this implies that a raised to the p minus 1 is equivalent to 1 mod p. It's truly a super useful result, and it will prove useful for us once more today. The second is Wilson's theorem, which says that p is prime is mutually implied with p minus 1 factorial being equivalent to -1 mod p. Now, these restrictions here seem a little bit harsh for me. I mean, the reason why we can't have 2 is because we want to assume that p minus 1 over 2 is a whole number. And the reason why we need p to be a prime is so we can use this direction of Wilson's theorem. And the reason why we want GCD of a and p to be 1 is so that we can use Fermat's little theorem and a whole lot of other necessary conclusions. So let's begin with the proof. So we will first assume that a is a quadratic residue. Now, what does that mean to be a quadratic residue? Well, it means there exists an x naught in this list, or this set, 1 to p minus 1, so the list of all the non-zero residues, such that x naught squared is equivalent to a mod p. Now, let's check very quickly if we can apply Fermat's little theorem. So the GCD of x naught and p is 1. Now, why is it 1? Well, p is a prime number, and x naught is a number such that p does not divide x naught, right? Because x naught is automatically less than p, so p cannot divide it. On the other hand, p is a prime, so every number that it doesn't divide, it's automatically coprime with. Therefore, we can use Fermat's little theorem and say that a to the p minus 1 over 2 is equal to x naught squared to the p minus 1 over 2, which is just x naught to the p minus 1. But since the GCD of x naught and p minus 1 or the x naught and p, is equal to 1, this expression is equivalent to 1 mod p. Perfect. Next, we will assume that A is a quadratic non-residue. Now, what does this mean? Well, this means that for all m in this list, m times x equivalent to A mod p has a unique solution such that x does not equal m. Because if x equaled m, then A would be a quadratic residue. So there exists a unique n in 1 to p minus 1, take away m, such that mn is equivalent to A mod p. Now, I want to point out that every single element this is true for. So we can index these equations. Mi times ni is equivalent to A mod p. I has to be less than or equal to p minus 1 over 2. If I were bigger, otherwise there mi and ni would not be unique to one another. And we can also say that p minus 1 over 2 has to be less than or equal to I. Otherwise, there exists an mi such that there is no solution. So just to hammer this point down a little bit more, we have our set 1, 2, 3, 4, 5, all the way to p minus 1. We're going to take an m1 and we're going to find, using its multiplicative inverse, so the GCD of m1 and p is 1, so therefore there exists a multiplicative inverse for m, which is unique. And we can solve this equation. M1x is equivalent to A. We can solve it by saying the inverse times A is equivalent to x, and then we're going to assign in 1 the value of this x. So let's say that it's 4 here. So now these two numbers can no longer solve the equivalency for any other number. So now we have to find some other m2 and say this is the n2 that solves it. Now we can go through this list and we cannot go more than p minus 1 over 2 times. So all this to say, I want to justify this conclusion. A to the p minus 1 over 2, that's equal to the product of I equals 1 to p minus 1 over 2 mi in I. Because each of these is equivalent to A, and we have p minus 1 over 2 pairs, and now we can finally apply all this jumbo that we were looking at to this equivalence. But according to Wilson's theorem, this is equivalent to negative 1 mod p. Now we can look at this briefly for Wilson's. Wilson's requires that p is prime, which we satisfied by our assumption. So we know that if A is a quadratic residue, A to the p minus 1 over 2 is equivalent to 1 mod p, and if A is a quadratic non-residue, then A to the p minus 1 is equivalent to negative 1 mod p. And we're done.